So, if you're a morel hunter, you are probably stepping right over one of the most, like, extreme athletes in the forest.
Oh, absolutely. People just walk right past them every single spring.
Right, you're out there scanning the dirt for those prized honeycomb caps, and you're completely ignoring this, plain, rubbery-looking brown saucer.
Yeah, the common brown cup. It is the ultimate example of why you can never, you know, judge a fungus by its cover.
Exactly. And today's deep dive is unpacking a stack of new research showing that this incredibly plain fungus is, well, secretly breaking aviation records.
And pulling off some truly bizarre chemical feats right under your boobs.
It's wild, but I mean, for over a century, mycologists basically just dismissed it.
Right. Much. Because it just looks like a generic brown cup growing on dead wood, it got lumped into this massive catch-all genus called Peziza.
Okay.
And it actually took modern DNA analysis in 2020 to reveal this cup was on its own unique evolutionary path. So they moved it into a highly specific genus called Philosopha.
I am kind of stuck on that initial shift, though. I mean, if it just looks like a standard saucer, what made anyone even think to look closer at its genetics in the first place?
Well, it actually started with some very strange chemical reactions out in the field. Mycologists use an iodine solution called Melter's reagent to test fungal tissues.
Right, to see how the tissue reacts.
Exactly. And usually those tissues turn blue or red. But when they applied it to the upper surface of this specific cup, the tissue turned this vivid, like blackish green.
Wait, blackish green, what does that actually mean mechanically for the fungus?
So it indicates a distinct, previously unrecognized chemical matrix in the tissue.
Oh, interesting.
Yeah, the fungus is structuring its cell walls using a totally unique carbohydrate makeup. And that separates it completely from the generic brown cups it was lumped in with.
Wow. Okay, but you mentioned earlier it breaks aviation records. How does a rubbery little cup do that?
That is the real reason it earned a new classification. It comes down to the violently extreme physics of its spores. The fungus essentially employs a microscopic spore gun.
A spore gun. Okay. How does that even work?
By utilizing internal osmotic pressure, the fungus basically builds a microscopic water balloon. It pumps sugars into a specialized cell, which causes water to just rush in.
Which builds up pressure, I'm guessing.
Immense internal turgor pressure. It builds and builds until the tip finally ruptures, blasting the spores into the air with an initial acceleration of 180,000 g-force.
180,000 Gs. I mean, humans pass out at what, 9?
Yeah, it's insane.
So it is literally a microscopic water rocket accelerating faster than a fighter jet. But, like, why go to all that effort just to launch a spore?
It's all to escape the boundary layer.
The boundary layer.
Right, there's this thin layer of completely still dead air resting right against the surface of the ground.
Okay.
If the fungus just dropped its spores, they would just sit there and fail to spread. It has to blast them through that still layer and up into the turbulent wind currents above.
Oh, wow.
Yeah, in terms of acceleration, it is the fastest documented flight in nature.
That blows my mind. But I have to imagine at those speeds, a standard biological cell would just get ripped apart by the air resistance.
That is the main challenge, yeah. Which is why the spores are custom built for the journey. Under a microscope, they are subfusiform.
Meaning they're shaped like slightly tapered footballs?
Exactly. Tapered footballs covered in fine warts. But most uniquely, they have these broad, flattened apical caps on the ends.
Oh, so those caps act like, what, aerodynamic stabilizers?
Precisely. They help them survive that violent launch and actually stick to their target once they land.
Okay, so it goes to all this trouble building a 180,000-gram water rocket with aerodynamic stabilizers just to land in a new spot. But what happens when it gets there?
Well, for decades, the assumption was that it just landed on a dead log and started eating.
Right, because you always see it growing on rotting logs.
Right.
So we categorized it as a simple saprobe, a decomposer.
That was the logical conclusion. But recent environmental DNA evidence completely flipped that script. We actually found it living directly on the living roots of oak and elm trees.
Hold on. It eats dead logs, but it is also attaching to living trees. Is it a parasite?
No, not at all. It acts as a facultative mycorrhizal partner.
Facultative meaning it has a choice.
You got it. It can break down tough woody tissues when it has to survive on a dead log, but when it encounters a living root, it flips a switch.
That is wild.
Yeah, it becomes a symbiotic partner, physically trading soil nutrients with the tree in exchange for sugars.
It's like being a grave robber who suddenly decides to moonlight as a life coach. I mean, it completely bridges the gap between decaying organic matter and living ecosystems.
It really forces us to question our basic assumptions about forest ecology. The most extraordinary survival mechanisms are so often disguised as the mundane.
It really makes you wonder, If this plain brown cup can secretly act as an ultra-fast, shape-shifting tree partner, what other boring organisms are living spectacular double lives right under our feet? Next time you're in the woods, look closely. You might just be looking at the forest's future life support system.